Hello, welcome to Module 2 for Immunology. Today we're going to talk about antigens and antibodies in the body and how they react together in the beginning, and then when we move on to the next chapter we're going to talk about how antigens and antibodies work together in the types of testing that we do in the immunology or serology laboratory. First thing we're going to discuss are the antigens. These are a substance that stimulate the antibody production and has the ability to bind to an antibody. For example, think of flu season. Flu season has a big incidence of the flu virus floating around. When your body becomes exposed to the influenza antigen, it in turn makes an antibody to help fight off that influenza virus in the future. Now, every year the flu virus changes, unfortunately, so if you get the flu one time, it doesn't mean that next year you're automatically protected. So therefore, flu vaccines, it's kind of a hit or miss. They try and put the correct antigens in there so that you're exposed and can create that antibody, but sometimes they're off a little bit because they don't know exactly which flu is going to hit. Usually they're pretty good at making sure they include the right ones that are going to be floating around for the next year, but occasionally those flu vaccines aren't as successful as what they would like them to be. The antigens are antigenic or immunogenic, which means they have the capability of provoking that immune response. So when you hear antigenic or immunogenic, that's what that means. There are also foreign substances that may contain antigenic structures. We have antigenic determinants or epitopes, and that is the part of the antigen that reacts specifically with the antibody or T cell receptor. So epitope and antigenic determinant are interchangeable terms that refer to the spot where the antibody interacts with the antigen. So what are some types of antigens of importance? Which ones do we really care about? Well, first of all, we have histocompatibility antigens. These are nucleated cells such as leukocytes that have cell surface protein antigens that provoke an immune response when put into someone else or another individual. Think of an organ transplant. If I were to receive a kidney from somebody else, that kidney in my body would recognize that as foreign and destroy it. So all of my organs have their own histocompatibility antigens on them so that my body doesn't fight itself. There are some undesirable effects of immunity called autoimmunity, which we'll talk about later on. But for the most part, your body does recognize itself as self, and it's able to recognize any transplanted organ coming into your body as non-self, which is, obviously undesirable in that situation. Then we have autoantigens. These are antibodies that may be produced in response to normal self-antigens. This would be the case of autoimmunity that I just mentioned. Thyroglobulin antibodies are an example. Thyroid autoantibodies in Hashimoto's disease, which we talked about in chemistry, are an example. And also diabetes type 1. Okay, sometimes we have autoantibodies to those islet cells. So those are examples of that. Other antigens of importance are the blood group antigens. So are you type A, are you type B, or are you type O? You're going to have a whole entire class coming up on immunohematology to learn these things. But for example, if you're a group A person, you have all these A antigens on the outside of your cells. If you're type B, you've got B antigens on the outside of your cells. If you're AB, you've got A and B. And if you're group O, you have nothing on the outside. Some of the properties of antigens, also called immunogens, which I mentioned earlier, is they're found as either proteins or large polysaccharides and rarely as lipids. If you want to be a good antigen, you want to be a protein. That's the most desirable trait to have. You must also have foreignness. You can't look similar to yourself. You kind of have to look different. Degradability. You have to have a higher molecular weight. The bigger the better. Structural stability, complexity, and be foreign so that it can be recognized as non-self. All right, moving on to antibodies. Antibodies are specific glycoproteins referred to as immunoglobulins. Sometimes we refer to gamma globulins as well. They function to combine with an antigen to aid in defense. After an antibody combines with an antigen, a secondary interaction occurs to dispose of those antigens, which is referred to as complement. We will discuss complement in detail during Module 5. We have 5 different classes of immunoglobulins: IgM, IgG, IgA, IgD, and IgE. They differ from each other in a number of ways, such as molecular weight, their sedimentation coefficients, and their carbohydrate content, and they vary within each class as well. We're going to go through each of these, and you will be responsible for knowing the differences between them. First one is IgG. This is the major immunoglobulin found in serum. It accounts for 70 to 75% of all immunoglobulins. It diffuses readily into extravascular spaces. It neutralizes toxins and binds microorganisms. It's the only one capable of crossing the placenta. It's very, very common in the secondary response, which we're going to talk about coming up here in a little bit. And when immunoglobulin complexes are formed, complement can be activated, which is the final destruction of the antigen cell. We find this increased in infectious diseases, other collagen disorders, and hematological disorders. We also have 4 subclasses, IgG1 through 4. IgG1 is more efficient at crossing the placenta. IgG4 is involved in allergies. I'm not looking at you guys being really very familiar with these. Just know there are other subtypes. IgM is only 10% of the immunoglobulin pool, but he is huge. As you can see the picture of him in the top right-hand side, he has 5 pieces coming out of him, so we refer to him as a pentamer. Pento means 5, kind of like the pentagon has 5 sides. This has 5 immunoglobulins coming out of it. It's produced very early in the immune response. It's very, very effective with agglutination and cytolytic reactions. We find this increased with infectious diseases, collagen disorders, and hematological disorders. I do have a chart coming up of the primary and secondary immune responses where you'll see IgG and IgM coming in. Next one is IgA. This one kind of looks like a crab. It's got 4 pieces, or 2 immunoglobulins stuck together, but you can see it looks like there's 4 sides on it. It's 15 to 20% of the immunoglobulin pool, and what's really important about this one is it's predominant in secretions such as tears, saliva, milk, and intestines. It's made by plasma cells, and it binds to a glycoprotein called the secretory piece in transport. It's increased in infectious diseases, collagen disorders, hematologic disorders, and liver disease. Next one, IgD. This one is found in the lowest concentration of all immunoglobulins. It's less than 1%. Its main claim to fame is it's bound to the surface of B lymphocytes. So you can see a little picture up there. There's a little B cell with a little IgD sticking out of it. Immunoglobulin E. This one, trace plasma protein found in the plasma. There's not a lot of it, but he's pretty powerful in mediating the hypersensitivity or allergic reactions, allergies, and anaphylaxis. What he does is he binds strongly to a receptor on mast cells and basophils. When that happens, it releases histamines and heparin from those cells. Those are the itchy sneezies, I call them, histamine and heparin. Notice when you have hay fever, everybody kind of gets that in May and June. You got all the new the dandelions and all those kinds of things coming up. That's when you start getting all the sneezy itchies. You take an antihistamine to try and suppress some of that so you don't feel so miserable. All right, looking at antibody structure, this is kind of a complicated page, but I'll show you a picture here in a minute. One region is referred to as the N-terminal end, is the variable region. We have different regions mediating binding of the Ig to the host tissues. I'll show you these in a second. Primary core consists of amino acid residues linked to by a peptide bond known as the constant region. We have 2 heavy chains and 2 light chains linked by a disulfide bond. Here we have it. So, looking at this down here, I just talked about the variable region, which is the end, okay, the little end tips. Then we have the constant region, okay, which doesn't change. We have 2 light chains and 2 heavy chains. So here's a light chain, here's a heavy chain, here's another heavy chain, and here's a light chain again. Usually there's 2 subtypes, kappa and lambda. Some people with certain types of disorders, they can have light chain diseases and such. that go into much more detail in immunology than I'm going to go into. The class and subclass of an immunoglobulin are determined by the constant region of the heavy chain. So this is what determines what type of class and subclass they are. The typical immunoglobulin consists of three globular regions. First, we got two Fab regions. The Fab region here is the antigen binding area. There is also an FC portion, which is, I call it the stalk, okay? And they're linked by a flexible hinge. There's a hinge area right in the middle here. Here's another picture that shows a little bit closer. The Fab site, which binds the antigen, is up here. The hinge region makes these arms flexible to be able to reach in and bind to the antigen. And then we do have the FC region here in the back. Other structures, we talked about the IgM having 5 subunits. IgA is a 4-chain structure. Remember, he kind of looks like a crab, has the little legs sticking out on the end per se. IgD looks very similar to IgG, and IgE looks very similar to IgG as well. We have different types of bonding inside of a antibody-antigen complex. The bonding of antigen to antibody is usually non-covalent, and there's different types of bonds involved. Hydrophobic, hydrogen, van der Waals forces, and electrostatic forces. So a lot of different types of bonds creating this reaction to happen. Another thing we have are immunoglobulin variants. So since immunoglobulins are proteins, they can function as antigens when we use them in an immunization type of situation. They're found in 3 categories of antigenic determinants. We have different types that they can create that are different. So an isotype means that there's differences in the constant region. An allotype means that there's differences in the constant and variable regions. And then idiotype is there's differences in the variable region. You do have to memorize what these different variances are for definitions. And this is how I kind of tell my students. Think of different people that are different become isolated. Variable and constant is all the regions are different. And idiotype is variable because idiots are variable people. So that's how my students taught me that. I didn't come up with that on my own, but that's how they've gone to memorize these 3 different types. All right, here's where I was going to talk about where IgG and IgM come into play for different antibody responses. We have the primary antibody response. Somebody who would have a primary antibody response would be the person who is exposed to hepatitis B for the first time. Okay. First thing that's going to happen is there's going to be a lag phase. The body's going to kind of hang out and be like, okay, something different's going on here. We don't have any antibody that's detectable yet. Then we have the log phase. This is where the antibody titer increases, which means there's an increase of actual antibody. We have a plateau phase where the antibody titer starts to stabilize, and then a decline when the body's starting to fight it off. The antibody becomes catabolized or destroyed. So a titer is the quantity of substance required to react with or correspond to amount of substance. Here's a picture. Primary response, we got the lag phase. We go up to the log phase, a plateau, and a decline. IgM comes in first. Okay, he's the primary player in the IgM. Then the body will start to make IgG. So IgM is able to come in and fight off initially, but IgG is more involved with being able to create a memory. Okay. Now the secondary response, which we're going to talk about in a minute, has a much shorter lag phase. Then it comes in much faster. IgM still comes in, but look at how much higher IgG comes in. He's the memory. So this time IgG, the body remembered, and it was able to spit IgG out faster. IgM always comes in, but IgG comes in faster with the secondary. So here's more information on your secondary response. It's exposure to the same antigen, an antibody response that exhibits the same 4 phases as the primary response, but shorter lag phase, longer plateau, and a more gradual decline. IgM is a principal antibody for primary, but IgG is a principal antibody for secondary. As I showed you, IgG is much larger here. Antibody titer, to attain a higher titer, plateau levels are tenfold the antibody response, so that it's able to come in faster and more powerful the second time you're exposed. It's usually, they say, you don't get the same cold twice, because your body's able to remember it. All right, we also have something called monoclonal antibodies. These are great for testing in the immunology and serology laboratory. These are created, they're cloned from a single cell, they have great purity and specificity. So let's say we want to create a test to test for Staph aureus. Okay, so we want to test for the Staph aureus antigen. So we create an antibody from the same cell, and we cause these cells to spew out identical copies of antibodies. So it's very pure and very specific. What we do is attach those antibodies to a latex bead, and we're able to create an agglutination, which we'll talk about in a little bit, where we can get all those cells to clump together so we can see a positive reaction that yes, Staph aureus is definitely present. Like I said, I'll show you some pictures of that coming up. So great uses we have for this is identifying and quantifying hormones. They're very difficult to pick up. Hormones is like a drop in a swimming pool, very difficult to detect because they're in such minute quantities. Attaching antibodies to them and then attaching a light source or something like that makes us able to see them. Typing tissue and blood, that's important. We're cross-matching in the blood bank. Identifying infectious agents, just like the staph that I just talked about. Identifying clusters of differentiation for leukemias and lymphomas. Immunotherapy, and identifying tumor antigens and autoantibodies. So we're able to actually look for people that may have certain tumors. Here's an example of what this looks like. They might immunize a mouse with a certain antigen, as you can see, and then they remove the spleen. They've got antibody producing cells. They're able to create from this and this whole process. You don't have to remember this process, but just know that there's a process that happens where they're able to create tons and tons of monoclonal or antibodies that are cloned from each other, which create a really good and specific test. All right, our next chapter is going to be agglutination methods. So what we do is if we have an antibody, we can have a test with an antigen in it, or if there's an antigen we're looking for, we can have a test with an antibody in it. When we get those to interact, we can create a visible reaction that we can see and know that that antibody or antigen is present. So let's look at this. All right, so what is agglutination? Precipitation and agglutination are the visible result of antigens and antibodies aggregating together. The first one is precipitation. This is formation of a solid mass from previously soluble components. Soluble means that they're in a liquid, you can't see them. A soluble antigen and a specific soluble antibody come together and create clumping that we can see. And it's very fine precipitation. Agglutination, the clumping or aggregation of particles that have antigens on their surface by antibodies that form bridges between antigenic determinants. We will see an example of this coming up in a couple slides. Usually we use something like latex beads or charcoal to attach the antigens or antibodies to. Coagglutination is just another way of saying that it uses antibodies bound to a particle. So that would be the charcoal or the latex. All right, so with latex agglutination, we have latex beads, as you can see over here. These are just round latex beads. Somehow the manufacturer is magically able to get a specific antibody, let's say antibodies to Staph aureus, to stick to these beads. As you can see down here, the antibodies are now stuck to the beads. When there's an antigen, we'll pretend these antigens here are Staph aureus bacteria, okay? They are going to bind via these epitopes or antigenic determinants you can see on the outside of the Staph aureus to those antibodies, okay? So in the next picture you can see antibodies stuck to the antigens, stuck to the latex beads, stuck to the antigen, stuck to the latex beads, etc. It creates a clumping. So we will have an actual visual clumping that we can see when we take the latex beads with the antibody, we mix it with a culture of potential Staph aureus. We may not know what it is until we mix it. If we mix it together, if they're compatible, it will create a latex agglutination, and this is what it'll look like. In part A, this is called a slide agglutination. It is negative on the right-hand side. There's no clumping here. On the left-hand side, it all clumped together, meaning it would be a positive result. On the right-hand side, we have tube agglutination. Okay, on the right-hand side, there is just a solid solution, It's just latex beads and culture mixed together, but nothing interacted because it wasn't compatible. On the left-hand side, the latex beads with the antibody reacted with the antigen and it made clumping, so you can actually see the clumping in the test tube. So that's agglutination. It's the antigen antibody coming together and creating those clumps. The next one is a flocculation test. It's based on the interaction of those soluble antigens and antibody, which form a precipitate, otherwise known as precipitation. Usually we can see them macroscopically, which means the naked eye. Sometimes you need a microscope. We have two variations of flocculation used in syphilis testing. For example, the VDRL and the RPR are tests that we use flocculation for. Then we have direct bacterial agglutination. This is what I talked about earlier with the Staph aureus and the latex beads. That's what this would be. Then we have something which confuses a lot of people, the indirect or passive hemagglutination. Hemagglutination refers to the agglutination of red blood cells. It's usually tested for antibody detection, and what we use are RBCs coated with a substance. It can be bacterial cells or fungus or protozoa. It's called indirect or passive because it isn't the antigen found on the RBCs, but the coated substance that the antibody will bind to. In other words, the antigen passively attached to the red blood cells being bound by antibodies. So that's hemagglutination. Here's an example. Antibody, red cell, and then we get the red cells and antibodies combining together. We have some factors that influence agglutination. We have two stages of agglutination. First is sensitization. It's the physical attachment of the antibody to the antigen. Then we have lattice formation, which cross-links between sensitized cells. So this is where we get the aggregation. It's the ability of a cell with attached antibody to come close enough to another cell for the antibodies to bridge the gap. What's important to take note of is zeta potential. If you've taken hematology, you know that all red cells have a net negative charge on the outside to repel them from each other so they don't stick together in the bloodstream. That can become a problem. So we have ways in the laboratory to overcome that zeta potential so the cells aren't always trying to repel each other. We want them to stick together. So in the lab we have to figure out ways to overlook that. Here's what we do. To enhance agglutination and overcome that zeta potential, we can use a centrifuge. We can attempt to overcome the distance between those sensitized cells by using a high gravitational force that will counteract that repulsion of zeta potential and physically force those cells to stick together and make that interaction happen. We can have treatment with enzymes. We can alter the zeta potential by stripping off that negative charge. That'll help sometimes. We can use colloids or anti-human globulin. This works with the antibodies that don't directly agglutinate RBCs by binding it with the antibody present on the RBC. We also have graded agglutination reactions, especially in a tube agglutination situation. The strength of agglutination is graded on a scale of 0 to 4. If there are no aggregates and it's completely negative, we call it a 0. Mixed field is having a few isolated aggregates, mostly free-floating cells, but your supernatant, which is the fluid that everything is floating in, appears red. So very, very hard to see. A weak means that you have, or plus minus sometimes it's called, tiny aggregates that are barely visible by the naked eye, many free RBCs, and turbid and red supernatant. So the supernatant again is what the liquid that you're looking at in the test tube. 1 plus is few small aggregates, 2 plus is medium sized, 3 plus is several large, and 4 plus is one solid aggregate clump. Here's another picture of looking at it in a tube rather than just reading it. You can see a 4 plus here, there's one big clump. Okay. 3 plus, there's several large clumps. 2 plus, we have a kind of a reddish background, but yet we do have some moderate clumps there. 1 plus, very difficult to see, but there are clumps there with a turbid background. And negative is there's no clumping at all. Sometimes we can have some interference, something called rouleau. I don't know if you've learned about this in hematology yet. If you haven't, you will. It's the false appearance of clumping. It looks like stacked coins or Rolos. So Rulo sounds like Rolo. If you ever had the candy Rolos, they're all stacked together. So Rulo and Rolo sound a lot alike. So when you hear Rulo, think of stacked Rolos, and you'll be on the right track. So you can see these red cells here are kind of stacked together. Okay, they're on both sides. That is Rulo. What happens sometimes, we call this pseudoagglutination. If somebody has a disease called Waldenstrom's macroglobulinemia, multiple myeloma, they get an excess of proteins in the bloodstream, which make it very difficult for zeta potential to occur. So you have excess proteins causing the cells to kind of stick together. And unfortunately, if you're don't have a trained eye, it may look like agglutination, but you look under the microscope and you'll look at this and say, oh, this is Rouleau. Usually what you have to do then is you have to wash the red blood cells better. I have a little thing here on pregnancy testing because sometimes we use antibodies for this. Monoclonal antibodies are directed against the beta subunit of HCG, and that's how we check to see if somebody's pregnant. So inside of the pregnancy test, there's HCG in the mom, and there's HCG antibodies inside the test kit. So when a pregnancy test is positive, the line will show up if there is antigen available. Usually serum concentrations of HCG are found right after conception. The test is negative. If it's negative, they usually repeat it. Peak levels are reached around 2 to 3 months after the last menstrual period, and false positives can occur with chorioepithelioma, hydatiform moles, and excessive ingestion of aspirin. Who knew? Okay, so then we also have agglutination inhibition. This is opposite of what you would think. If agglutination is present, it means that the test is negative. Okay, this isn't used very commonly, but if you do hear agglutination inhibition, just know that if agglutination is present, the test is negative. Okay, so if this were to be used in pregnancy testing, it neutralizes the antibody and there's no agglutination present. If no HCG is present, agglutination occurs between the anti-HCG and the latex, and that would be a negative result. Here's an example. We have antibodies and a live hemagglutinating virus. We bring them together. On the right side, there's no antigen-antibody binding, and on the left side, there is antigen-antibody binding. We introduce the red blood cells, and if it mixes, or if the antigen antibody reaction happened, the RBCs are free floating, they have nothing to bind to. If it binds up all of the virus, that means you will have agglutination present. So it's opposite of what you would think. Now there's also latex agglutination slide tests and enzyme immunoassays and things used for pregnancy testing. A little bit easier to use. We'll be using a lot of these types of tests, especially like strep tests, throughout the quarter. And that concludes Module 2.